Many of you, as Robin mentioned, I was very fortunate to be able to come and visit during the early onsets and early years of the development of this project in the center, and got to meet many of the graduate students as they were getting their projects off the ground. So it's been fun to see the progress of the students and the projects, and looking forward to those research papers coming out there, and then hopefully for industry, for you all to pick up some of these amazing graduate students for jobs in the future. I think that would be great. So again, my name is Dr. Channah Rock. I'm a water quality specialist at the University of Arizona. Today I'm going to be talking about water, and I know we're all challenged with dealing with water in the agriculture setting of recent years, especially related to some of the policy decisions that have been made. And so oftentimes I find myself at the interface between industry and policy and trying to build up scientific data to support industry and to support future regulation, but in a place that makes sense for both, and in a place that makes sense to protect public health while also helping industry grow safe and nutritious products. So again, I appreciate it today. So let's see if I can get going. So evidence tells us that we should pay attention to water sources as potential vectors for pathogens. So vector meaning that it can move pathogens in and around the environment. If we look at the unfortunate outbreak in 2018 that was tied to E. coli 157H7 linked to romaine, this was largely linked to the Yuma growing region where I am. If we look at the FDA and CDC report, there were linkages related to contaminated irrigation canals as the most likely sources of that pathogen in that specific outbreak. However, there were questions related to how the pathogen got into the irrigation system in the first place. Did it come from adjacent land use or something occurring upstream? Or more localized. And then there were lots of hypotheses related to the application of potentially contaminated water to produce within that growing region, and what made it different about this year. There were some hypotheses related to freeze event and damage to frozen product and the potential for these lesions or wounds on the leaf surface, specifically romaine, and the ability to harbor pathogens that might have been present in that agricultural irrigation water. A more recent example also in the US, and I'm sure there's plenty of examples from across the world and produce in Australia as well. This example comes to us from Florida, more recently a different pathogen, Cyclospora, in which FDA has found Cyclospora in irrigation canals and districts adjacent to potentially implicated fields in those Cyclospora outbreaks. So again, if you were to go into the literature and to pull out historical examples, there's plenty of information that either points to or links agriculture irrigation water to the potential presence and spread of pathogens into produce. So we know specifically surface waters are of higher risk than other water sources, whether that be domestic water supplied by a city or town that might be treated, or groundwater that might be pumped up into a reservoir or directly for irrigation. So we know that E. coli is potentially there, but where did it come from? Oftentimes, we break contamination into these three different groups. So obviously people, unfortunately, people are gross and do gross things out in the environment, especially when they're recreating. So that's something that we teach growers to what to pay attention to. Additionally, wild or domestic animals, we often look at adjacent land use, what may or may not be occurring on adjacent land use for in and around produce. And then are there legal or illegal discharges in waters upstream of ag irrigation? So again, plenty of different opportunities for potential pathogens to make their way into a water course. So one of the things that is good about the environment is that it allows or provides an additional retention time. So that allows those opportunities for attenuation or die off of those microbial contaminants. So that can certainly be helpful. As we all know, those microbes like that perfect, warm body temperature and anoxic or oxic conditions to survive. And so if we think about survival of microorganisms in the environment, we certainly have to consider things like temperature, light, oxygen, nutrients, all of those things and their ability to survive or to die off over time. Additionally, if we also think about surface water specifically, we think about things like rain and runoff. Fortunately, where I'm located in the US, Arizona, there's very little rain or runoff, and so that's good from an overland flow perspective. However, in different parts of the country and the world where there is extensive rain or runoff, you can certainly see tracking of rainfall and runoff with microbial loading in some certain locations. So things to pay attention to with relation to water and water contamination. In a study that we conducted a few years ago, we were tracking and trying to marry up microbial water quality sampling and bacterial loading with other types of parameters. And so for the specific region that we were looking at and looking at E. coli and Salmonella, we saw linkages between precipitation, temperature, electrical conductivity or salinity, and sediment to bacterial loading. So depending upon the different time of year and depending upon what we saw as far as precipitation, temperature, EC, and sediment, we were able to design some predictive values to be able to share with industry about the potential for bacterial loading in those regions. So while that can be helpful, certainly it doesn't account for all different types of scenarios. And so because of that, we've seen a recent push with local regulations, whether that be commodity specific regulations and also national FDA regulations, really trying to hone in and focus on water, irrigation water quality, and what they deem as appropriate or inappropriate for produce irrigation. So, you know, if we think about water as a food safety issue, most of the metrics we've seen thus far are intended to prioritize risk by really trying to classify a water system and classify that use. So as I said earlier, you know, depending upon the way that the water is applied, the irrigation type, for example, if that's furrow versus drip versus overhead application, that's potentially going to have different risks associated with that. Same goes if the different water type, if you're using a surface water versus a groundwater versus a municipal water, there's different risks associated. So what we've seen in the metrics is the assignment of risk based on those different factors. Additionally, and what the LGMAs, I'll get into that in a second, have really outlined is a find and fix structure, really to help the ag industry identify nonconformities or more serious failures, fix them and retest them and to confirm. Really what we don't want is to see a failure, kick somebody out completely and not have a path for them to rectify that failure and to come back into compliance. And so we work really closely with industry to design corrective actions and to design mitigation structures so that they're being able to come back into compliance. And really, if we go overline the metrics that I'll talk about here in a second, they really should be considered the minimum controls necessary to assess ag water systems, really for fitness of use. So they can be a starting place for industry, but certainly not an ending place related to how they should assess their agricultural water. So those of you who are in leafy greens produce may or may not be aware of the Arizona and California Leafy Greens Marketing Agreement. This was originally brought about in 2006, 2007, when growers came together to raise the bar on food safety. At that time, agricultural water was within that original agreement, and it talked about assessing the acceptability of agricultural water for ag irrigation. They had assigned some numeric criteria, so some values of generic E. coli bacteria for different irrigation types. More recently, in 2013, we've seen the passing of the Food Safety Modernization Act. So basically the standards for growing, harvesting, packing, and holding of produce, FSMA for short, by the FDA. While the original regulations passed under FDA did have numeric criteria for generic E. coli in water, those are still pending. So those have yet to be finalized. So I have the two values up there on the screen, the 126 and the 410. What we know is that that will likely change. We've been waiting for a while to see what FDA releases. But in the meantime, we've been teaching and working with industry to evaluate their water sources, to look at these values and compare their current water quality to these values to see, well, would you meet this or would you not? But we do know from FDA is that any future regulations that we see related to water are not going to be as difficult as these two values. So again, we will wait and see what happens. We heard late this year, we're running out of days for FDA to be able to provide feedback to us, but we'll see. However, because of the more recent outbreaks, specifically tied to leafy greens in Arizona and California, the LGMAs in 2019, so last year, provided a new water metric or a revision to the previous water metric. In this metric, they assigned two different types of water, type A if you're groundwater or municipal, type B if you are surface water. Related to this, if you are within 21 days of harvest and overhead irrigation and using a type B or a surface water, you have to prove non-detect of generic E. coli. So essentially we went from a surface water requirement that you have to have, acceptable water quality with a low level of generic E. coli. They've now moved to basically drinking water quality with a non-detect generic E. coli. So as you can imagine, this can be challenging for certain regions growing leafy greens. One of the big ways that industry overcomes this challenge is related to the use of US EPA approved sanitizers for agriculture water treatment. So I've been working probably over the last 10 years related to agriculture water treatments, a variety of different treatment technologies. Currently, we're funded right now through the Center for Produce Safety to conduct a multi-regional study related to ag water treatments. But there's some very specific challenges that industry must face related to EPA approved sanitizers. So unfortunately, most of the EPA approved sanitizers that we have available for industry are not necessarily labeled for their use in produce or labeled for their use against human pathogens. So they may be labeled for their use against biofilm formation, or they may be labeled for indicators, but not necessarily labeled for pathogens themselves. Related to that, and because industry, is faced with this huge challenge of being able to meet non-detect, EPA and FDA recently worked together. This was released in July of 2020, so just recently, released a new protocol for the development and registration of treatments for pre-harvest ag water. So basically, they developed a test protocol that industry can use, so sanitizer companies can use to evaluate the effectiveness of their products on human health pathogens. So they have 2 S-Tech strains, 7 Salmonella strains, and 5 Listeria strains that now must be evaluated against to receive a new updated label for their use in agriculture water. So as you can imagine, this is a new feat, new challenging information for industry. So one of the things that is most challenging about this is that the acceptance criteria under the new labeling scheme says that the results should demonstrate a minimum of 3 log reduction of each of those test organisms as compared to the control. So is 3 log feasible? How does that compare with drinking water and wastewater treatment for the use of these similar chemistries? What are the current log reduction values in agriculture for these treatment chemistries? So much of our research currently is focused specifically on that. If we look at disinfectant effectiveness, specifically for bacteria, I've highlighted these all in red, and we look at those disinfectants along the top, you see chlorine versus ozone versus UV light. All are generally good or excellent, quote unquote excellent, for bacterial removal. However, if you come down here at the bottom and look at typical dose, you see that there are quite a variability or range in the appropriate dose of a chemical disinfectant to achieve the appropriate log reduction. So again, challenges that industry are facing right now are trying to decide, which chemistry is going to work best for me in my area. It's important to remember that chemical disinfection isn't instantaneous. And so I think that's the thing that we work with industry the most, reminding them that disinfection or inactivation depends on 5 different factors. So first, who are you trying to kill? Is it a pathogen or an indicator? 2, the dose or the chemical concentration. 3, the contact time. So how much time does that chemical have in contact with that bacteria or virus or other pathogen in water? 4th is the temperature of the water, which can be challenging, right? If you're in an industry and you're irrigating out in the open environment, that's not necessarily something that you can control. And likewise, the 5th is pH of the water. So again, can be more challenging for industry to be able to control. So I won't read through all of these. Hopefully my slides will be shared later, but we can kind of go through some of the issues or problems related to those 5 different factors or factors that can influence water treatments and potentially some of the solutions that we're working on with industry. I just put this up there to remind folks that sometimes when customers say, well, just treat your water and you'll be fine, it's much more complex than that and much more challenging. So how does an industry representative or grower choose a water treatment method? Again, it's a variety of different questions that they're asking themselves beyond just the chemistry that they're selecting. Thinking about, well, who's going to be the person in charge of this? Are they adequately trained? What about discharge into the environment? What about crop sensitivity? So there's many laundry lists of questions that we're working with industry to try to overcome. So here's a list of the most commonly used water treatment chemicals or devices. We break them up into 2 different groups, either a pesticide device, and you see those listed there, or a chemical. The ones that are most commonly used, I've highlighted in red here. We see a lot of use of any of the chlorine derivatives, also the sodium or calcium hypochlorite, peroxyacetic acid as well. So certainly those are the ones that we see used more. Because of some questions about short and long-term soil health and stability, we've started to see the potential introduction of alternatives such as UV light. However, there's a lot of issues that has to overcome as well related to energy usage, glass in the field, and contact time. So those are generally the biggest issues. So will it work? So what are the things that we're working on with industries? First and foremost, identifying, well, what's the pathogen loading or what's the indicator loading in your source water? So how well do we have to treat that water? What is that contact time and how can we narrow in on your dosing requirement? But again, as I said, it's more than just that. It's these other issues related to equipment costs, worker safety, ease of use and testing, and setup and design. So we've seen the progression of folks who've been treating for a while, where they've started versus kind of where they've ended. I'll quickly go through a little bit of data and then I'll wrap up my presentation. I know you have a busy schedule today. So here's some data from a recent test that we did. I have 2 treatments, treatment A and treatment B. We have total coliform bacteria on the left-hand side. The blue bars are the background total coliform bacteria. The red bars are samples taken at different time points at the first sprinkler head, and the purple bars are at the last sprinkler head. So basically what you can see here is that it takes some time for that disinfectant to make it to that last sprinkler head. You have to purge all of that water in that distribution system. And then even though we've maintained residual, we still see breakthrough at that first sprinkler head. So water treatment is not consistent and it can be variable. Here's another real life grower scenario. We have the green bar is pH, the aqua bar is chlorine residual. And as you can see, when they turn on their chlorine dose and get that chlorine started, and then all of a sudden they turn on a sulfur burner to help modify pH, that chlorine is very quickly consumed. And so again, this is a real world scenario where a grower is trying to conduct fertigation, conduct pH amendment, and water treatment, and they're not all consistent. They're not all working together to achieve what you'd hope in the end for water treatment. Some of the more pressing questions that we're getting from industry are related to disinfection byproducts. So these can be formed during disinfection. Generally, these happen when you have chlorine that can interact with organic matter. And we've got some questions about the use of chlorine in water treatment with high organic loading and DBPs over time. Additionally, we have questions about short, medium, and long-term impacts of water treatment on microbial communities. So looking at the microbiome or that community of organisms in these productive lands. And we've recently been taking microbiome samples from the rhizosphere and the phyllosphere. So basically the soil that's in and around the roots of the plant, as well as the plant itself. And here's some images of plant tissue, water samples, root zone, and soil core sampling for our CPS project, pre and post treatment. So we've been tracking fields over time and looking at changes in the microbiome to really try and better understand what is going on with the microbial communities over time. So some of the recent research and research results, we know that sanitizers and disinfectants don't kill microbes instantaneously. We've seen breakthrough of those targets after system stabilization. And so it's really trying to understand the system that you've designed and how well it will work for you and how to troubleshoot when you do see problems. We know that not every water that touches a crop after treatment is treated. But we generally like to say that water treatment isn't a hazard elimination, but rather a risk reduction, and try to perpetuate that dialogue amongst industry and amongst regulators so that we can start to see, well, what is really going to work. And so we have growers that have, been forced to implement ag water treatment, regardless if that ties in with risk or risk assessment or not, but they are up for the challenge. So I thought my last couple slides, this is from a grower here in the Yuma region. They've set up a water treatment device that's got a blinking light that tells them that that water is being sanitized. Often they're irrigating in the middle of the night or through the night. So they're faced with a challenge and they're meeting that, and they're meeting it well, and they're happy to share more information about that. So again, I like to say a grower is an agronomist, entomologist, a climatologist, a soil scientist, a microbiologist, and now a water treatment operator. So hopefully what we can do is build up the scientific data that can help them be better water treatment operators, and to help build that knowledge to inform some of the policy decisions that are being forced upon them. So with that, I know that we're short on time. I appreciate the opportunity to speak to you all today. I hope you have a wonderful Industry Day and conference. I'm looking forward to the student presentations, and thank you all so much.
Well, thank you, Channah, very much for that wonderful talk. It's quite a lot has changed. Sorry, I'll just put my video on. Right, quite a lot has changed over the last few years, particularly with those recent outbreaks with romaine, and it's meant huge challenges for the industry to produce a safe product. I'd like to invite questions. If you would like to either do it through the Q&A button or the chat button at the bottom of your screen, please feel free to ask questions of Channah. We've got a little bit of time to do that. Channah, irrigation, overhead irrigation, is that here to stay, or do you think there's a possibility that they might be able to move away from overhead irrigation, because that would solve a lot of the challenges?
Yeah, that's a great question, Robin. I think that in certain parts of the growing regions, that furrow or flood or drip irrigation are likely options. However, in other regions, sprinkler and overhead is likely what we'll continue to see. One of the things we've also seen recently, and again, related to some of our research related to furrow irrigation, is that we've also seen some customers start to put pressure on furrow treatment. I'm not necessarily an advocate of treating all furrow water. I think that's very challenging and might defeat the purpose of furrow irrigation in the first place, but that's certainly been brought up. So I think we have a lot more questions related to risk reduction and what is really acceptable, and do we need to be treating every drop of water that touches, you know, the surface of the crop? Can we mitigate those risks in other ways?
Right.
So it looks like we have a question. What should surface water versus groundwater be tested for? How often? Drop irrigation of tree nuts. Yep. So great question. So depending upon the metrics that are being followed, if it's related to FSMA, or the Food Safety Modernization Act, depending upon your water source, dictates how you need to be testing that water. So that might change, but you would imagine surface water you need to be testing more frequently. It's about 20 samples over a period of 5 years. For groundwater, you need to take 5 samples and 1 additional sample each subsequent year. So a lot less, because that's less risk. Generally, the samples are analyzed for generic E. coli bacteria and for total coliform bacteria. So right now, no pathogen testing in irrigation water, but indicator testing. So hopefully that answered the question.
So Channah, I guess one of the other things that's been puzzling for us is the proximity of intensive animal production close to these sorts of enterprises. Are you working with those industries to try and get some solution so that they don't sort of run off into rivers and into etc.? What's the cooperation that's going on in that area?
Yeah, so it's challenging. So currently, I don't believe under FSMA that there are any specific distance regulations related to adjacent land use.
Mm-hmm.
However, in the LGMAs, it's a 2-mile distance from concentrated animal feeding operations. So that's the currently designated setback distance. And then dependent upon the customer, that may be bigger, that may be smaller. And so I think what we're trying to do now is look at, well, what data is out there. You know, where did 2 miles come from? Was that just, you know, plucked out of the sky and trying to implement that? And what are the real risks associated to different animal agriculture? I think because potential for runoff or discharge is a really big issue. A lot of discussions are trying to be built to have conversations with produce growers and with animal growers, and get those 2 groups in the same room to have conversation. Later on in your agenda, Michelle J. Russell can talk quite a bit about some of the work that she's done to try to bring those 2 communities together to have that conversation.
Yeah, difficult one. Thanks very much, Channah. Are there any other quick questions, very quickly? If not, we'll say a very big thank you to Channah for joining us. It's not morning for her, it's going on for the evening, so we're very grateful that she's been able to join us for this presentation. And if there are any other follow-up questions, we'll forward them through to you. Hopefully you'll be able to see some more of the presentations later on.
Absolutely.
Thanks very much, Channah.
Have a great conference. So
we'll reconvene at 11 o'clock where we've got the PhD student presentations, and there's a new link to join us for that. So we look forward to seeing you there. Thanks very much.